This is the Chapter 31 textbook companion, and it should be pretty short. I mean, there's only one section here. It's more like the gravy. It's just to explain why people would be interested in nuclear physics and some of the applications there. Okay, so let's start with fission. If you remember from last chapter, we saw this graph where you can see that as you add nucleons to a nucleus, they, on average, each one gets happier and happier. And this is huge happiness. We're talking about millions of electron volts worth of energy that can be released as you fuse things together, and for elements that are these huge unwieldy masses of, oh, I'm on the wrong layer. Okay, so these huge masses, this would be something like, you know, U-235, so 92 protons and, you know, 150 or so neutrons, just huge masses. You can split these up, and as they become two smaller blobs of nucleons, each nucleon on average is happier that way. And so this is called fission. It's not that many elements that can undergo this, even though they would all like to. But U-235 is one if it absorbs one more neutron and becomes U-236. Suddenly it's so much less stable. It's a crazy world. Okay. It's so much less stable, and within a fraction of a second it's going to split into two lighter elements. Okay, so with the wonders of copy and paste, I've created all of these big unwieldy uranium atoms. They're these little guys. And this is one that's in the process of fissioning, of splitting into two separate clumps of nucleons. What happens when that occurs is you get neutrons that are given off. On average for uranium you get about 2.5. So it might be 1, it might be 4, it might be 5, whatever you get. You look at the average of them, and on average it's 2.5 per fission reaction. Now also per fission reaction, if you look here, you get two fragments that are happier. Each nucleon is happier by about a mega electron volt. But look, we've got 200 nucleons that are now that much happier, and so we get about 200 mega electron volts released in this one reaction. It's really crazy. All right, well, it gets more interesting if one of these neutrons from this fission event gets absorbed by another atom. When that happens, then, okay, so let's say this goes here and gets absorbed. Then this begins to fission. It will give off neutrons. Those neutrons can be absorbed by its neighbor, and you get what's called a chain reaction. This is a nuclear chain reaction. So all you need for a critical chain reaction, you need one neutron per reaction absorbed by U-235 in this case. It's U-236 that changes. So once it absorbs a neutron, or yes, U-235 absorbs a neutron and becomes the changeable, the fissionable U-236. All right. So when you talk about getting material for, say, a critical chain reaction, like in a bomb where you want it to be supercritical, or in a reactor where you just want to use this energy for creating electricity, for example, then you need to purify the uranium sample so that you have less of the uranium-238 isotope, which will also absorb neutrons, but it doesn't immediately fission like U-236 does, and so it poisons the reaction, right? So 1 neutron per reaction needs to be absorbed by U-235. And when this happens, when you've got your geometry in such a way, so let's zoom way out. Let's say that I've got this chunk of U-235. I've got the big enough mass that on average 1 neutron from each fission is being absorbed by one other U-235 atom. That's called a critical mass. So critical mass, because that's the critical point where you get a chain reaction happening. And if you get more than a critical mass, that's the reaction will go supercritical, is what you say, and will quickly run out of control unless you have a way to control it. Okay. So for a bomb, that's all you need is a supercritical or a critical mass or more. You cut off a piece of it so that it's not critical while you're moving the bomb. You have some conventional explosives that knock the piece into the other piece, and it suddenly becomes a critical mass, and the bomb explodes. That's an atomic bomb. Atom, because you're using the energy stored in the nucleus. I mean, a better way to say it is a nuclear bomb, because all bombs are based on atoms. Most bombs are based on chemical reactions. These happen to be based on nuclear reactions. And so you get, millions of times more energy out per reaction than with TNT or even with my beloved butter. Okay. All right, and here's my drawing of a reactor. So you can see this is the reactor building. It's got this cooling tower where you can send your steam and water. You run it through pipes around the outside of it. And then that condenses so that you can reuse it as steam. Okay, but the source of heat is actually this nuclear reaction that we've been talking about. It sits in this tank of water. This is the normal way that we do it in the United States anyway. It sits in a tank of water as these reactions are happening, and you have all of this energy that you get from the missing mass from each reaction. That's given as kinetic energy to this water, so it heats it up, comes along here, gives its heat to some more water in a separate pipe. You do that just to keep the radioactive stuff out if there's a leak in here. You got steam that turns a turbine back to, electricity created by moving a magnet next to a coil. And then the steam is exhausted, and you cool it so you can reuse it. All right. Now, if you zoom in on this reactor, the core of the reactor, what you've got are fuel rods. That's these little things. They usually have something that's pretty transparent to neutrons, but doesn't let the nastiness that is the fission fragments, the yellow and blue here. They're extremely radioactive. The reason for that is, if you remember, you have, sorry, I meant to do Z here, and neutrons here, neutron number. There's a line that for low elements, you find all the stable elements right along that line. But then as you get to heavier and heavier, it bends off, and you usually find stable isotopes with more neutrons than protons, which makes sense because you're not fighting as much Coulomb repulsion, and you still have a lot of the strong nuclear force, the glue that holds them together. Well, look, if you take this, something right here like uranium-235, and you split it into two pieces like this, they're no longer on the curve of stability. I guess they wouldn't be quite that far. So they want to get back to stability, and they start doing it by radioactive decay. That's some more energy that gets released in these reactions inside the fuel rod. But you want to keep it contained, so you cover them with a metal cladding, is what it's called. And if you look inside a fuel rod, you would see these little pellets. They're about 1 centimeter long, so they're not huge. They're made out of the uranium. Normally, you enrich to about 5% to 15% even U-235. And the rest is U-238. And, I mean, to get to weapons grade, so that you have a smaller critical mass, you normally enrich to, up to 80 to 90% uranium-235. So you can normally tell if a country's telling the truth, if they just want it for civilian use or if they really want to develop a weapon, based on how highly they can enrich uranium with the setup that they've invested in. Okay, so these up here are called control rods, and they control the reaction. You can raise them and lower them. Raising them has the effect of increasing the reaction, because these are usually made out of something that absorbs neutrons really well, like beryllium, for example. As the neutrons come across, if they hit the neutron absorber, then they'll just stay there and they can't be absorbed by another fuel rod's U-235. And so you slow down the reaction when you insert the control rods. As you remove them, then the neutrons are free to go between control rods and you get a hotter reaction. Now this water acts not only as something to absorb the energy that's being released by this reaction and transfer it over to here, it also acts as a neutron moderator. So a neutron that gets emitted here from one of these all the way back, one of these reactions, will bounce off of water molecules and slow down until they call it thermalization. It doesn't have millions of electron volts of kinetic energy anymore. Now it's just got, less than an electron volt, so hardly any of the original kinetic energy. So it transfers the energy to the water, but now it's traveling more slowly, and so if you are a neutron and you're thinking about falling into a strong nuclear well, the slower you're going, the more likely it is that you get absorbed. And so it also has the effect of making the neutrons more easily absorbed by the reaction. So this is called a moderator. This is a water-moderated reaction. The thing that slows the neutrons down to where they can be easily captured is called the moderator. Now the other side of this reaction is where you get energy by fusing things together. As you push them into bigger and bigger clumps, they get more and more happy, so they release energy. This is what happens in stars. There's something called the proton-proton cycle, where you get two protons that basically form deuterium and release a positron as well. And then the deuterium can be fused into helium, the helium into, what's the next, beryllium? Is that? I think so. Yeah, that has 4 protons. And then you can get, when you finally have enough of these alpha particles around, enough of these helium nuclei in heavy stars, you can get them to fuse together all at once and form carbon. So carbon-12 is formed this way. And once you have carbon, for reasons we won't go into, then it's really easy to burn through the hydrogen. It acts like a nuclear catalyst, basically. And you can take carbon, take it through nitrogen and oxygen and back to carbon, and on the way create an alpha particle out of just protons. So that's an efficient way to convert it. The proton-proton cycle is not very efficient. It takes a lot longer. Anyway, that probably doesn't matter to you unless you want to study the way stars evolve. But it's kind of interesting to think about the reaction rates changing the way, how long stars exist, basically. Now, the natural question to ask at this point is, couldn't we use fusion to make our energy instead of fission? If we had a nuclear reactor that worked by fusion, all you would have are maybe some neutrons that it releases. You would have helium, which is a good thing for science, actually. So you'd release helium. None of this nastiness that is completely unstable. These are stable isotopes. Neutrons will decay into hydrogen after not too long. Well, the issue is not creating fusion, because we can do that. The issue is then getting the energy back out, containing the fusion, and keeping it going for long enough that that the reaction gives back as much energy as you put in to start the reaction. Fission is easy that way. I mean, this can happen basically at room temperature. I mean, this isn't at room temperature, but you get the idea. We don't need millions of degrees to start fission. It just happens spontaneously because it wants to. Fusion, to get over the barrier that's formed because protons hate other protons, and helium hates protons even more than protons hate protons. So to get over that Coulomb repulsion and the wall that it forms, you need to have millions of degrees in order for that fusion to start. So the next question you might ask is, can you use fusion for weapons? And yes, we do. So you can start a bomb with fission. So you start it with conventional explosives to start a fission reaction. The fission reaction, if it gets to be a runaway supercritical reaction, can create the temperatures needed for fusion. And so you include in your bomb enough nuclear fusion fuel to then be fused by this fission reaction, and you get even more released energy by the bomb. And that's called a hydrogen bomb. Hydrogen, because you put a bunch of deuterium and actually tritium, which isn't shown here, which would have 2 neutrons and a proton. You put that fuel in there, and the fission reaction starts the fusion reaction.